Hello guys, let's talk about a special kind of language is called regular language. As an introduction, you may pause the video and try to create a NFA or DFA for this language. I'm not sure how much time you spent, but after some struggling, we find out that, yeah, we cannot construct such machine for A to the n, B to the n, which is our famous language. Why this should happen for a simple language like A to the n, B to the n? That's a very important question. So here is the reason. We know that A to the n, B to the n is equivalent to lambda AB, A square, B square, and so forth. It means that all of the strings have equal number of A's and B's. But the question is, how can we count the number of A's and make sure that have the same number of B's? Okay, so if you create a machine, then the machine should be able to count the number of A's, right? But we don't have any counter here. Not only we need a counter, we need a storage to store the number of A's, and when we reach the B's, we need to count number of B's and to make sure that these two numbers are the same. So that's how we can accept a string like this. But how can we do that? DFAs and NFAs don't have counter. They don't have storage. That's the problem. Okay, so we just realized that there are different kinds of formal languages. Whatever we have seen so far, really, they didn't need any storage or counter. But when we reach a simple language whose pattern looks like very simple, A to the n, B to the n, then we realize that, hey, DFAs and NFA cannot accept them. So it looks like this guy is more complex than whatever we have seen so far. We realize that some languages are more complex than the others, and also we learn that NFAs and DFAs have limited power and they cannot recognize if we have more complex language. One way to study formal languages is to categorize them. Okay, based on our previous slide knowledge, we can construct DFA or NFA for some languages and we cannot for the others. So we can categorize them like this. If this is the set of all formal languages, then we have some languages here that we can construct DFA or NFA for them, and we have some languages like here that we cannot. One language that so far we have learned is A to the n, B to the n. Okay, so let's give this portion a name because these portions are very important formal languages. We call them regular languages. So here is the definition of the regular language. A language is called regular if there exists a DFA or an FA to recognize it. So in other words, the rest of them will be non-regular. Okay, so here we have regular languages and here we have non-regular languages. All right. We have already learned that the association between machines and languages are very important, and we saw such things. So if this is the set of all automata machines and this is the set of all formal languages, every set of machines will associate to some portion of the languages. And we just learned that DFAs and NFAs are associated to this portion that we just call them regular languages. Okay, so now let's review another categorization we had before. We learned that languages can be finite or infinite. This was our first categorization for the formal languages. Now we have learned that we have regular languages and non-regular languages. Okay? But yeah, just please note that we know the correct English word for non-regular is irregular. We know that. But computer scientists, for some, let's say, unknown reasons to me, picked the non-regular for the irregular. Okay, now let me ask very important question. How can we prove that a language is regular? We just need to construct a DFA or NFA for that. Just pay attention to this point that this is not a mathematical way to prove. We will provide some mathematical ways later, but for now, we just try to construct a DFA or an FA. You may say, okay, I cannot, create an NFA or DFA for something, so maybe you don't have enough skill, right? So we would need a mathematical way to prove that. Okay, so now let's look at some examples that mostly we have seen so far. So is this a regular language? Yeah, we constructed a DFA and NFA for them. How about this one? How about this one? This one? This one? And this one, even this one, we created NFA or DFA for all of these languages, so it means that all of them are regular. I put an exercise for you here. Here is the language. AWA is the pattern, and I ask, first of all, create a set builder for that, and then prove that L square is regular. Before giving the mathematical proof for recognizing the regular languages, I'm going to give you a heuristic way to find out whether a language is regular or not. So let me explain it via this example. Okay, the question is this a regular language? We look at the pattern, we say A, B, and then everything. We ask ourselves, do we need a counter or do we need storage for this? Not really. It's very easy language. We can construct a DFA. So definitely this is regular. How about this one? Oh, that's a very important language. The pattern is W, W reverse. Before I can answer this question whether this is irregular or not, first I need to understand what kind of strings this language contain. It is saying that the strings have two parts. The first part and second part are reverse of each other. So in other words, if I want to enumerate this language, I would get, let's say for example, AA. And if you divide it into two parts, this guy and this guy are reverse of each other. Actually, A and A, yeah, maybe you don't have any feeling here. Let me take another example. For example, ABBA. If you divide it into two half, then you see that this is RW and this is W reverse. So first part and second part should be reverse of each other. So all of the strings of this language should have the same feature. So now you understand why I said A and A are part of this language, because A is just one symbol and its reverse is itself. And how about this guy? For example, A B B B B A. Yeah, if you cut into two half, you see that if this is W, this is the W reverse. So first part and second part should be reverse of each other. Based on this knowledge, now my question is this a regular language? Definitely not. Because first of all, I need to be able to divide it in two halves. And then I need to record the first part, and then I need to compare the second part with the first part to make sure that they are reverse of each other. How can I do that with DFAs or NFAs? It is impossible. So that's why we would say, yeah, this is non-regular. Definitely, this guy is non-regular. How about the next one? WW. What is the difference between this and the previous one? The previous one, both half should be reverse of each other. This guy, both half should be exactly equal. And again, we have no feature in DFAs and NFAs to do that. So just as an example, this WW, for example, AA, is part of that. ABAB, BABA. So as you see, we need to cut them into two halves, and then each half should be exactly equal to the next half. So definitely this is not regular, or in other words, non-regular language. How about this one? The same as WW, it just added, BB here, but this part and this part should be exactly equivalent. So this is non-regular. How about this one? 1 to the 2k, k greater than or equal to 0. Oh, this is the even number of ones, and we could construct a DFA, and this was actually as our solved problems before. So this is regular. So as you see, how can we heuristically figure out that a language is regular or non-regular? And how about the last one? All of the strings looks like this. And as you remember, this is a unary addition. All of the strings of this guy should look like this. For example, 1 plus 1 equal to 1, 1. 1 plus 1, 1 equal to 1, 1, 1. All of this one is one string, right? So do I need a counter? Yes, I need. How can I figure out that 1 plus 1, 1, I would need three ones here. So I would need a counter to count this guy and to make sure that the result is exactly the same as addition of the first two. So definitely we would need storage, we would need counter, and this is non-regular language. Now let's study finite languages. We have a theorem for finite languages that says all finite languages are regular. Very interesting. Why is that? How can I prove this? But before that, let me convert this plain English statement of this theorem to a logical format. All finite languages are regular. It can be converted logically. If L is finite, then L is regular. This is the logical format of this plain English statement. How can I prove this? I need to construct a DFA or NFA for a finite language. Okay, let me pick this language L equal to S1, S2, and up to Sn as a finite language. And all of these S's are just regular strings. Okay, so if I can construct a DFA or NFA for this language, then that would be a proof for this theorem. But just note that S1, S2 to Sn, they are expressed very generally. I cannot take example. I need to prove that in general. How can I do that? The proof starts from here. I can construct an NFA for every string. What does it mean? I know that a string is a finite sequence of the symbols. That's the definition of strings. So finite number of the symbols, I am claiming that I can construct one NFA for that. Let me take an example to show you what do I mean. Here is an example, ABB, which is a finite sequence of symbols. Can I construct an NFA for that? Yeah, it's so simple. A, B, B, and it will be accepted here. I am using NFA because NFA is more flexible, okay? But I can, of course, construct a DFA for that as well. So if this is the case, then let me construct an NFA for one of these S's. Let's say, for example, SK, which is in the middle of this and it's a general string. SK has a finite number of symbols like this. A1, A2, let's assume that A1, A2 up to AM are just alphabet, right? So SK is a finite sequence of this alphabet. Can I construct an NFA for that? Of course I can. So simple. You see, A1, A2, up to AM, and it will be accepted here. So for the SK, I could construct an NFA. For simplicity, let me show it like this box. So this box is an NFA to accept only one string SK. Okay, now the question is, can I do it for other ones, for S1, for S2, for up to Sn? Of course. If I could construct an FA to accept S index K, which was a general one, definitely I can construct for all of them. And let's assume that this is an NFA for only accepting S1. This one is for S2 and blah, 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 up to here, which is S index N. So all of these machines were constructed to accept S1 up to Sn. But I don't need separate machines. I need to combine them and prove that all of these strings can be accepted, because I need one NFA for the whole language, right? So now my job is to combine them. How can I combine them? And here is the role of lambda transition. I can put a Q0 or initial state here and connect all of this with lambda transition and put all of this inside the box and say, hey, this is a machine which happened to be NFA, and I claim that this NFA can accept all of these strings. But how it is possible? Can you explain this? Of course we can. It's so easy. When I put S1 here, what would happen? S1 goes here, and based on the content of the S1, we might have several processes, and at least one of those that goes this way will accept S1 because we constructed this machine for S1. So we are sure that different processes will be created for that, but at least one of them goes this way and S1 will accept that. All right. And how about S2? Yeah, we are sure that S2 will goes here. One of those processes goes here and will be accepted here. Okay. And up to S to the n. So it means that this NFA can accept S1, S2 up to Sn. So we proved that that language L equal to S1 up to Sn, we can construct for it an NFA. And that's how we prove that all of the finite languages are regular. In math, we learn this equivalency. So P implies Q is equivalent to negation of Q implies negation of P. So it means that I need to negate this guy. This will imply negation of the P. This is a logical relationship for implication. It means that if this is a theorem, its contrapositive is correct too, right? We just proved that if L is finite, then L is regular. How can I make its contrapositive? Yeah, I need to rename them. So L is finite is P, so this is P and this is Q. And this P implies Q. If I use this contrapositive equivalency, then what I get negation of Q, which is this guy. If L is non-regular, then L is negation of finite, is infinite. So in other words, if L is non-regular, L is infinite. And if I translate this to plain English, it means all non-regular languages are infinite. This is another face of the theorem that we just proved. Let's get back to our formal languages categorization. We learned two categorizes so far, and one of them is finite and infinite that we show like this. So this is the infinite part, this is the finite part. All right. Now the question is, where can I locate the regular and non-regular? This portion, we just had a theorem that says all of the finite languages are regular. So definitely this part is regular. But how about this part? All of the infinite languages are non-regular, or some of them are really regular. For example, a language like this, a to the n greater than or equal to 0, we can construct a machine for that, an NFA or DFA for that. So it means that this guy is regular. Okay, so what's the conclusion? It's not the case that all of the infinite languages are non-regular. Some portion of that should be regular. So in other words, regular languages occupy all of the finite languages and a portion of the infinite languages. Something like this. After we learn what regular languages are, now let's talk a little bit about their properties. Here I have some theorems that they are called closure property of regular languages. Okay, so here is the theorem. If L, L1, and L2, all of them are regular language, then the result of the following operations will produce regular language. What does it mean? It means that if L1 is regular, L2 is regular, if we union them, we will have a regular language. If we complement them or reverse them or concatenate them or intersection minus and something that here is called L star that I didn't cover in the videos will produce regular languages. So it means that the family of the regular languages is closed under the above operators. To prove these theorems, we would need to construct NFAs for them. And we use NFAs for most of them because, as you know, NFAs are more flexible. But before going further, let me introduce a very useful transformation that will be used in all of the proofs. And that utility is how to convert an NFA that has multiple accepting state to only one accepting state. How can I do that? It's very easy by that magical lambda transition. We just need to convert these accepting states. It can be any number of the accepting state. We just make them as a regular state like this, and then we create one accepting state here, and we connect all of those that originally were accepting state with a lambda transition to this new one. And as you know, Q, whatever it is now short-circuited to this new accepting state. And in fact, they are the same. In other words, if a string halt here, since they are short-circuited, it can jump to here and will be accepted. All right. By this technique, we can convert any NFAs who has multiple accepting state to only one accepting state or single accept state. Okay, now let's get back to our proofs. Let's start with the simple one. L1 and L2 are regular, and we want to prove that L1 union L2 is regular. How can I prove that? I need to prove that I can construct an NFA for L1 union L2. Let's call it, for example, L. Okay, how can I do that? It's so simple. Yeah. So since L1 is a regular language, I can construct an NFA for that. So let's call it M1. L2 is a regular language. I can construct an NFA for that. Let's call this M2. But how can I prove that L1 union L2 is a regular language? I need to construct an NFA for that. How can we do that? Just combine these two like this. I create a initial state here. This was the original initial state for M1. This was the original initial state for M2. I made them as a regular state, create an extra initial state, and you can guess that we connect this new initial state with lambda to the original one. Okay, and if we consider the entire this as a new machine, we claim that this machine will accept L1 union L2. How come? Because the strings of this language, L1 union L2, are coming either from L1 or L2. Okay, so because this is a union, right? And if we put, for example, a string from L1, yeah, there might be several processes, but for sure we know that one of them goes this way and will be accepted here, because this machine was constructed for L1. So any string for L1, we are sure that via one of those processes that might be created goes that way and will be accepted here. And the same thing, the strings from L2, we are sure that goes this way and will be accepted here. So in this way, all of the strings of L1 union L2 will be accepted by this machine. So this machine is actually an NFA for L1 union L2. This theorem is saying that if L is regular, then its complement is regular too. How can we prove this? First of all, we need to convert the NFAs that we just talked, that we need to make it as a single accepting state. You need to convert it with the technique that we can convert any NFAs to a DFA, because this theorem and the algorithm that we are gonna introduce work only for DFAs. And here is how we can prove that L bar is regular. So if this is a DFA for L, then we already know an algorithm that we can convert this DFA in such a way that it accepts L bar. What was that algorithm? We change the accepting states to regular states, and we change the regular states to accepting states. So since we have a solid algorithm that can work on all DFAs, it means that this is a mathematical proof that if L is regular, L bar is regular too. If I can construct a DFA for L, I can construct a DFA for L bar as well. Now, to show you that why that algorithm works only for DFAs, not for NFAs, here is some counterexample. This is an NFA for this language, L equal to empty set. This is an NFA because you don't see any trap. If we convert this regular state to accepting state, it becomes such thing. But the point is, this is not the L bar, yeah? The L bar of this should accept everything, but this guy is accepting only lambda. So this is a counterexample that shows if you apply that algorithm for NFAs, it does not work. I mean, it does not produce L bar for that. Now let's create a DFA for the same language, L equal to phi. This is the DFA, okay? Now we apply that algorithm. We convert all of the regular states to accepting state. And is this the case that this is the L bar of this L? The L bar of this L should accept everything. And this DFA is accepting everything. For this theorem, we are going to prove that if L is regular, then L reverse is regular too. What is L reverse here? So let's take some example to refresh your mind. For example, if we have AB and let's say ABB or I don't know, BAA, something like this, and so forth. What is the L reverse here? We need to reverse all of these strings. So this will be BA, this will be BBA, this will be AAB, and so forth. So all of the strings should be reversed. Okay, now the question is, how can I prove that L is regular, then L reverse is regular? So if this guy is regular, I need to prove that this guy is regular too. So since L is regular, I can construct an NFA for this. So let's assume that this is my machine for L. Now the question is, how can I convert this machine in such a way that instead of accepting AB, it should accept BA, right? I put AB here, machine reaches here. Do you agree that if I reverse these transitions and then make this guy as an accepting state and this guy as an initial state, of course we need to convert this to a regular state. And if I put BA here, the machine goes backward and accept the BA here. Yeah, that's true. That's true. So here is the algorithm I'm gonna propose here for proving that if L is regular, then L reverse is regular too. So first we assume that since L is regular, we can construct an NFA for that, and let's assume this is an NFA. Now we apply this simple algorithm. We reverse all of the transition. We change the initial state to accepting state. We change the accepting state to initial state. And just remember that this is an NFA that we applied that transformation that converted it to single accept state. Okay, so that's the only way that we can have only one accepting state. And when we want to convert it to initial state, we make sure that machine has one and only one initial state. So this is how we prove that if L is regular, L reverse is regular by proposing this algorithm that can be applicable for all of the NFAs. Next theorem is regarding the concatenation. If L1 and L2 are regular languages, we want to prove that if we concatenate these two languages, the result will be regular too. To refresh your mind, let's assume L1 is AAB and L2 is another simple language, let's say, for example, BB and ABB, something like that. And what is the concatenation between L1 and L2? All of the strings of L1 should be concatenated to all strings of L2 like this. A, B, B, A, B, B, A, B, 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 and A, B, B. So this is the concatenation of these two languages. Now, if we have an NFA for L1 and we have an NFA for L2, how can we combine them to construct a new machine that accepts L1 concatenated with L2? So just look at this string. This string is coming from L1 and this string is coming from L2. And this is true for all of these strings. So one part is coming from the L1, the second part is coming from the L2. So do you agree that if I just make a sequence of these two NFAs, then we can construct a new machine to accept L1 concatenate with L2? Yeah, let me show you how it works, okay? So let's assume this is the machine for L1. I need to make this change here. The single accept state here, I make it as a regular state like this. And then this machine is for accepting L2. I just connect used to be accepting state, but now it's a regular state with lambda to the initial state and M2. And if I put a box around this combination, I believe that this guy, this new machine, will accept L1, L2. How come? Because as I took examples, let's say, for example, A, B, B, if I remember correctly, so this A was coming from L1 and this coming from the L2. So since this machine is for L1, so I confirm that this string that is coming from L1 should reach us here and used to be accepted here. So the A should reach us here, and since this lambda is short circuit between these two, then machine jumps to here and will accept the rest of that, which is ABB, which is coming from the second language, and M2 was created for accepting the second language. This way we can analyze and we can prove that all of the strings of L1 concatenated with L2 will be accepted by this new machine. For some theorems, we don't need even construct a machine. For example, for intersection, look at this. L1 and L2 are regular. We want to prove that L1 intersect with L2 is regular too. I need to construct a machine for L1 intersect with L2, but I can play with mathematics and with all of the theorem that we have proved so far to use them to prove this one. How? So easy. Look at this. L1 intersect with L2 is equivalent to this by De Morgan's law. So instead of I work on this, I work on this one. L1 bar union L2 bar and a complete bar over all of them. This equivalency is coming from the De Morgan's law. Since L1 and L2 are regular, then L1 bar based on one of those theorems that we already proved is regular. L2 bar is regular too. Also, we had one theorem that says union between two regular is regular. And we know that if we have a regular language, the bar will create another regular language. Since this guy is regular and it is equivalent to this, so it means that L1 intersect with L2 is regular too. We can have the same place for the minus. L1 and L2 are regular. We want to prove that L1 minus L2 is regular too. In this case, we will be using this equivalency. L1 minus L2 is equal to L1 intersect with L2 bar. And you know that. How can I prove this is a regular language? Right? Because L1 and L2 are regular language. L2 bar is regular language. L1 intersect with L2 bar is a regular language. And since this guy is equivalent to L1 minus L2, therefore L1 minus L2 is regular language. Now, let me ask this final question. What is the next step? In this lecture, we have learned that we have regular languages, what regular languages are. We proved some theorems about them. Now we are sure that this portion that we are so familiar with it, which are called regular languages, we can only construct DFA and NFAs for them. So, in other words, there are infinite language here that we call them non-regular, and we still don't have any machine for them. One of them that is very famous is A to the N, B to the N. This language, we struggled to construct a DFA or NFA for that, and we couldn't, and we know what the reason was. I'm gonna stop here. See you guys in the next lecture.